Would someone like to volunteer? The 2 math workshop problems, number 5 and number 6. I have a hand up at table 2, so let's go with it, table 2.
Okay, so number 5.
Okay.
10k squared minus 3k plus.
Give your group a point. Okay, so she combined the 6 and the 4. That's how she got 10k squared. 2k, negative 5k, she got negative 3k. And then the plus 9. With a different group, like to answer question 6. Yes, go ahead, table 1. I had 2 different hands up, either one.
Negative b squared minus ab minus 2.
Okay, and I believe he is correct, but again, as discussed last week, negatives have always been my downfall in life. They tend to get me in trouble. If negatives tend to get you in trouble as well, I suggest you distribute the negative. So I would have written what I'm going to write in blue, where I actually distribute that negative and get negative 2b squared and minus 2ab. Then when you combine those like terms, yes, positive 1, negative 2, I do get a negative 1b squared. Yes, positive ab, negative 2ab, I do get negative ab. He is completely correct. Maybe he is a genius and automatically got the red. I have to do the blue in order to make sure my life stays right. Table 2, or table 1, I forgot to tell you to get a point on that, didn't I? So you should have your point. Yes, ma'am. That would be awesome, but if you're super duper duper lazy, which is fine, I understand, you can just put what table number. Although, is there a slight chance I would forget you sit at table 4? Possibly. Possibly. Okay, so last week we folded a piece of paper in half, and that piece of paper said discrete and continuous on it. That's all we did, though, is we folded it in half. And then we said we're done. So before we even start looking at it, let's talk about what you should have done when your mama said, hey, what are you learning in discrete? What's something you could have told her based off what we were talking about last week? Computer science. Okay, I heard 2 and 4 say computer science, so give yourself a point for that. Table 1 has its hand raised, just here. It is in the, were you here Friday? Did I not give you one somehow? I think there are more in the Friday if you want to look in the discrete bucket. If not, I'll give you mine. Okay, so I heard computer science. There are more words that you could use. I would give points. There are other words. What are you learning in discrete? Table 1 can get a point for that. Sure. Table 4 had a thought.
Stuff you don't think will benefit us in college.
Yes, that is true. I'm hoping for an actual topic, but that is true. Give yourself a point for that. And then
Counting techniques.
counting techniques. Okay, table 2. Table 2. And then table 1 had their hand raised. So go ahead, table 1.
Umbrella of real world situation. Real world top.
That is the darn trick. So you can get a point for that. Yes, it is. 11. Don't confuse me. Okay, so I'm done with those 3 points for that. I swear there's tons more 3 points you can earn. So let's face it, you took discrete for a reason. I don't know what you're scared of. You're either scared of pre-cal or cal. I'm not sure. It depends on who you are. I read through your index cards. Different situations for different people. You were scared of pre-cal and cal, and they live in the world of continuous, which is good. So you came here, the world of discrete. Clearly, we are 2 different worlds. So good for you. You decided you didn't want to go there, so you decided to come live here with me in discrete. That's great. Today we're going to discuss their similarities and their differences, so we can connect kind of what you were supposed to learn at Algebra 2 with Treg to some of the stuff we're going to talk about in here. Okay, so a continuous graph is a graph that is, and we've got to figure out a word to put. Yeah, I'm not going to put continuous. I'm actually going to pick a different word. It does keep going. I know I got a special vocab term. I got a really silly vocab term, and you're going to guess it in just a second. So you agree my two graphs look pretty similar. They both look like linear functions. I just put some random dots. And you're going to say, okay, they look a little too similar, Miss Compton. What's the difference between them? On one of them, we're not going to connect the dots. On the other one, we are going to connect the dots. In the world you've been living in, the dots have been connected, haven't they? So my blank is going to be connected. It's in the discrete on the 13th, or what? No, the 11th, right? Yeah. Connected. So you've been talking about functions that had connected graphs, where when you put dots, you got to actually connect them. And it was great. You're used to connecting the dots. In discrete, we don't get to connect the dots. So we have a graph that consists of, I'm going to say distinct, and then what's the other word I'm going to use? Distinct points. Table 4, get your point. Okay, and what do we mean by distinct points? That means that, for instance, this red one is clearly different from and separate from this blue one. And if I were to describe it, I would say the red one is 1 to the right of the axis, and you would say, well, the blue one's 2 to the right of the axis. They're clearly two different things, separate points. The way we are separate people. Okay, and if you've got that, you already know what's coming next. Flip open your book. Now, if you are not cute like me and you don't like having a cute little flip book, when we get done with the notes, if you want to punch the holes in it and stick it in your binder like usual, totally understand. I'm telling you, you took discrete for a reason, because you wanted to be fun and color, so we tend to be cute with our notes. Sometimes we're boring, but we tend to be a little on the cute side. Okay, so we're going to graph discrete and continuous functions and try to look at the differences between them. Our first example with both is the line y equals 2x minus 1. How do we graph that line?
The 1 is our y-intercept. The negative is the y-intercept.
Yes, it is table 4. You can have your point for that.
So is the slope.
And what does that mean?
It means it's like the rise over run thing, so it goes up to
Up to over 1.
then over 1.
Okay, up to everyone, up to everyone. I already gave you a group of point for that y-intercept, so I'm not going to give you one for that, but that was good. That was good, good, good. And then, I should do it in a different color. I'm going to do the exact same thing over here. Except I swear for the most part today I can read. And there is a slight difference between the two problems. Besides the fact, like we just talked about, on the right graph I get to connect the dots. On the left graph I don't get to connect the dots. That's one difference. And then there's another difference between the two problems in the wording of the problems. How did they describe the domain of this one?
Oh.
They said it was
Greater than or equal to x.
bigger than or equal to 0. So that's why I started here at 0 and went up 2 over 1, up 2 over 1, up 2 over 1. Or I started here, geez Louise, at the point 0, negative 1. But on this one, they actually told me specifically to go down to negative 1. So I went on the x-axis to negative 1, and I still graphed that point. So this one has an extra point that that graph doesn't have. And the only reason why I gave this graph an extra point is because the directions said to.
If we're taking a test and that's on there, and we don't throw the extra point down, are you going to take off for it?
Well, that's a good question. And my gut would be, no, baby. But the answer is really probably yes, because of this next part. It says, identify the range. I tend to be a nice tester. In discrete, you'll learn if you just use your words and explain yourself, I tend to give you points. Okay, so it says we have to identify the range on either of these graphs. Do you remember what the word range means?
Is it like negative infinity?
There was infinities involved sometimes, but domain was for a certain thing and range was for a certain other thing.
Here's the
One is
pin.
up and one is sorry.
How high or what how it's fall.
Ooh, I like the how high or how low.
Is it the X and Y?
Yeah, the range was the f of x, or you would say the y values, and the domain was the x values. So they gave us the x values, but you and I reading this graph can figure out the y values. Now, if you really wanted to go back, and I mean back to like Algebra 1 back, you used to make a table, and you would say, okay, I'm going to plug in -1. Well, my function is 2. Everywhere I see an x, I put -1, -1. And then when I actually evaluate that, I figure out my y value. So -2 minus 1 is -3. And then you would do the same thing with all the other points. You would keep on going. And you can always do that. But most of us don't want to. We can just read straight from this graph. We can see that at -1, our range is at -3. At 0, we're at -1. At 1, we're at 1. What's our value at 2? Table, I don't know which table to give it to, so I'm going to hold it in. And then at 3, it is.
5.
Okay, and then I heard it from everyone. So you know what? Everyone can have a point for that. Okay, that was pretty easy. All we had to do was really read the ordered pair. So like this ordered pair was 0, -1. So that's why 0 and -1 are both the second entries in our list. Like that really wasn't that hard. It gets a little harder with what you were doing in Algebra 2 with trig. In Algebra 2 with trig, there were negative infinities involved and positive infinities, and you had to know if you were driving along the y-axis is what I always told my kids. So just as a refresher, or at least this is how I explain it, let me preface. We're not going to do a lot of domain and range here in discrete. So if that gets you down, I understand. To be honest, don't tell my AP Cal teacher. I didn't know what the crap she meant every time she said it. I used to just guess negative infinity to infinity because I did not know what those words meant. So now that I figured it out, I'm happy. It does appear a lot on standardized tests. Domain is x values, and normally most people can figure that out. Range with the y values seems to be a little harder. I always think about hell and heaven, and that if I'm driving along the y-axis from hell and I'm going up to heaven, like when can I actually reach out and touch my graph? Like if I need to grab onto my graph, when could I actually touch it? And I start touching it here. Like I could touch it there. And then I keep driving and I can reach out and touch it here, 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 here. I keep on touching it. And I can touch it from then on out. So my range starts actually at what value? Okay, it's y greater than or equal to what number?
0.
Where did we actually touch it at?
-1.
We started touching at -1. So from -1 on up, from -1 all the way up till heaven, we could keep on reaching out and touching our graph. And you would say, but Miss Compton, on our last one we made a list. How come we can't make a list on this one? That's a good question. And it's because, and this is really silly, but it's because we connected the dots. When we connected the dots, because it was a continuous function, we stopped just allowing it at the points. So we can reach out and touch it at 1, yeah, that's true. But heck, we can reach out and touch it at 1.5. We can touch it at 2, that's true, but heck, we can touch it at 3 3/4. We can touch it anywhere from -1 on to infinity. I could say, hey, try to touch it at 5.25, and you could try. So that's why our range is actually an interval rather than a whole list. So one reason you'll love discrete, we tend to be, like the word says, discrete, like a list of things. Okay, now we're going to do the exact same thing, but with a different function. So -x plus 4, can someone help me graph it? It is going to be going the other way, give you a point. Someone help me graph it. I need help graphing. Is the slope? Yes. Where did I put that intercept at?
4.
Okay. I put my intercept at 4. And I go down 1/1, and he's right. It's leaning a different way. And before you get too carried away, especially if you're using pen like me, I have made a mistake. I need you to help me fix it. In fact, I'll make another mistake. Here, I'll go over here and make some mistakes too while I'm at it. Okay, can someone help me correct my mistake? Ma'am?
I did exactly what you did. You're supposed to go to the negative side. Because it's a negative one.
Yeah, I did. -1 and up here. -2 and up here.
So would you not go
4 is on
over and down on that on the
I put my point at 4, and then I went down 1 over, went down 1 over, went like you told me to.
but on the other side?
I think I put my point at 4 and went down 1 over 1 like he told me to. I think he's right with his graphing. I think I'm wrong with my reading. I think I didn't read the directions. Table 5, you can get a point for that. Okay, so back to, and this is what you were asking earlier. You were asking if you would get counted off for this. I would right now. It says specifically -2 to 2. So I did -2 in that one. So -1, 0, 1, 2. I should not have this point or this point on my graph because that's at 3 and that's at 4. The direction said -2 to 2. I didn't follow directions because, you know, we're used to it. I kept on going. And because I did that, I'm going to end up having more values in my range. Okay. Can someone help me with the range of this graph? If you need to be driving from hell to heaven, you can. Or if you just want to tell me the ordered pair, the other number, that would be easier. Say it again, ma'am. 2, 3, 4, 5. You may get a point for that. Okay, she's had her Wheaties this morning. I have not. I did not see that at first. I was counting. I said, okay, well, I went up 1, 2, 3, 4, 5, 6. So I know one point in the range was 6. I went up 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. 1, 2. And then I was like, oh, she is right. It's 2 through 6. She just put it in the right numerical order. Whereas I was paying attention to the graph. So she wins. Yay. She wins. I don't know what you win, but you win. You already got a point. What else do you want? Are there any questions on this one? Okay, and then we look over at this one, and again, Miss Compton's made a mistake. I did not pay attention to my domain. Greater than or equal to 1. So how many points do I have on my graph right now that are wrong? Let me zoom in for you. 2 points that are wrong. Did you say that? You may get a point, table 1. I shouldn't have that one there, and I shouldn't have that one there. I was supposed to start at 1, and I did from here on out. But those 2 points would have changed my range. So I need to pay more attention in life. And I can't spell range. That's even better. Or range.
But why would you follow the equation instead of
Because I read that with domain this. If they didn't put with domain that, I would totally have done it before. I totally would have. I
So you
agree.
just totally ignore the
Well, the equation helps me get the line, but yes, would I erase those 2 points? Yes. Is this all silly? Somewhat. Okay, so I connect my dots because this is a continuous function. She doesn't like the nitpickiness of the domain. Totally agreed. Is life normally this hard with the domain? No. We're specifically proving a point that discrete functions get continuous functions, but like that's what we're trying to prove right now. Okay, the range, we're driving from hell to heaven. Like, in hell, I could probably reach out and touch that red graph. Of course, the graph's red and I'm in hell. I can probably reach out and touch that red graph. But eventually, as I start getting closer and closer to heaven, at some point, like, I can't reach out and touch it anymore. Where is that point? On the y-axis, where can I no longer reach out? Positive 3. So our range is anything below positive 3. As long as we stay under 3, we can reach out and touch it all day long. But anything higher, and we're SOL. Okay, and then you're like, my God, Miss Compton, I purposely took discrete because I didn't want to graph anything else like this. Totally understand. Again, we're trying to prove a point today that discrete functions are so much easier because they're, I'm able to touch it, is what I feel like. There's a specific list. I know I'm right. It's just easier. So we're proving that point with the graphs. We are going to have a checkpoint tomorrow, but on the checkpoint is going to be stuff like our following 4 examples. This is what we do in discrete, is here is a word problem, explain this. So we're given 4 different situations. Good Lord. It's like the longer I go in the day, the more slurred I get. We're given 4 situations. Yeah, don't be concerned. It's just water, I swear. We're given 4 situations, and we have to explain why the situation is either discrete or continuous. So our first situation says, like, here's the cost of movie tickets. Here's a little number of movie tickets and the cost. I need reasons why that specific example is a discrete example. Any thoughts on that?
There's no pattern.
Price. 5, right? 5 at a point. Price is a set number. That's one thing we could write. The price of per ticket is a set number, and you're going to pay $8.50 for a ticket regardless. She's not wrong. There's nothing wrong with what she said, but we all have our own thoughts, and that's kind of the whole beauty of discrete, is that you get to have your own thoughts and your own words. So someone give me some other words. Tell me the pattern.
It goes like $8.50 to $7, $25.50, 3, 4.
Okay, they're adding $8.50 each time. Say it again. Proportional. I like that. Set pattern person, add a point to your group, and proportional, add a point. Yes, table 4, you had your hand up.
This tickets are going up in there. I was stretching, so.
That is true. There is something I'm wanting you to notice about this, yes. Or the price is set with back to a certain amount of movie tickets cost a certain amount of money. I get that. I mean, you could have worded it like that.
Yeah.
I'm hoping someone's going to talk to me more about the number of movie tickets. I need you to use common sense and tell me about when you go to the movie theater, you can't
You can't get like, I don't know if this is right, like 1.5. It's like,
Add a point to your group. Yeah, you can't buy half a movie ticket. I know this sounds really silly, but a lot of discrete stuff is rather common sense stuff. Like, you can't buy half a movie ticket or a fourth of a movie ticket. Like, hey, I just want to watch the second half of whatever movie you're playing. Can I just give you $4 and that be okay? It's not going to work. Maybe y'all know someone working at Amstar, I don't know. But when I go, you're either paying for the full movie or you're not. And back to the beauty of discrete and of my grading is that, so she has her own thoughts and he has his own thoughts and they have theirs. And yeah, your groups might look similar to yours because you talk to them, I get that. But my God, surely you use different English words. God gave you such a great vocab. Okay, are there any questions on this one? Do you have to list all of things all in time? No. Any of those answers were sufficient, I think. But maybe all together they make a complete, coherent unit. Okay, then we get to this fishing tank experiment, which kind of creeps me out because I don't know why they're decreasing the temperature of the tank, but it is what it is. Okay, so I need to know why this example is a continuous example and not a discrete example.
there's no header.
Table 1, you get a point. Okay, there's no pattern, meaning it's going -3 degrees, -1 degree, -2 degrees, -3 degrees. I can't bank the next one's going to be -1 degree. I can't. I don't have enough data to make that kind of an assumption. It does start with time, like, you know, they didn't take it and then they gave it an hour. The 0 I'm actually okay with. No, I keep going, keep guessing. That's good. Tell me more.
As there's more time going up, the temperature goes down. So there's like a correlation between the two.
There is a correlation, but I think we're purposely turning down the temperature, which again is kind of creepy. Like, what are we doing to the fish? But that's another thought entirely. That's another thought entirely. He was thinking something about temperature. I'm with you. Something about temperature. Tell me what's finicky. What's weird about temperature?
Why is it going down?
You can get like you can get to negative degrees.
You can't get to negative degrees. Table 2 said what I was thinking, so I'm going to give Table 2 the point. In that temperature is kind of hard to pinpoint. Right now I can count. There are 4 plus 4 plus 4 plus 4. That's 16 people plus me. That's 17 people in this room. I can count. The temperature, I can change it within seconds by turning that thing on or off. So temperature is kind of hard to measure. Temp, hard to... You're going to have the thought. I'm ready for you to have it. Temperature's hard to measure exactly. You've watched the weather lady. You know she just kind of guesses. She says today's high is between 80 and 85, and you're like, oh, okay. And then they'll take it over so long in the day, and they'll say, well, yesterday on average the temperature was 83. But, I mean, even the weather lady, she doesn't know exactly how hot it's going to be today until today's already happened.
The range or mode.
The only other thing I'm waiting to hear before I move on to the next one in life is something to do with the time. It does go by hours. Do we have to go by hours? What could we do?
Go by minutes.
You could go, oh my God, he's going to sit all day at the tank. Okay, good for him. I'm not doing it by minutes. Any other thoughts? You could go 2 hours, 3 hours. You could go every 30 minutes. You could go every 10 minutes. So back to, you could check the tank. You could check the tank.
Stop worrying about fish temperatures. Do something productive.
I know. At different. And I'm going to tell you a secret that I forgot to tell last period, so you're getting a little more for your money than they are. If it tends to be time is finicky. Time is finicky. It's like measuring temperature. Like, are you going to say it's exactly this time? Like, my clock says what time do you say it is? 154, and that one says 154 for now. They're not exact. I don't know. Time is like temperature. It's kind of wishy-washy. It's not like when I count how many people are in this room and I can put my hands on it. Okay, let's go to our next example. So 5th grade now wants to go play laser tag because of this one example, this one time of laser tag. So we're going to go play laser tag. Here are the points. Why is this necessarily a discrete function?
It's a pattern. Every hit is worth a point.
Okay, table 2 get a point. That's fine. You can keep going. So again, he's noticed that every single time you score, you kill, I guess you kill someone when you score, you get 4 more points. +4. It's a +4. It's tiny and ugly, but I just wrote +4 in between each one because it was increasing by +4 each time. Every time you hit a target, your score goes up by 4 points.
You can't skip like the target number, like up top.
That's true. So, I'm going to say no gaps, because I'm going to take what he said and rephrase it differently. No gaps between targets, hits. So either I hit Brittany or I don't hit Brittany. There's no I almost hit Brittany. Either I'm getting my 4 points or I'm not getting my 4 points. It's a hit or miss. And then someone last period who clearly plays basketball said something, and there's no assist, so you can't get a 1 point because I kind of helped you set this up. There's nothing like that here. And basketball really wouldn't work in this situation anyway, because basketball, you're not scoring by a certain number each time. You can get 3 points, you get 2 points. If it's free throw, you can get 1 point. So this whole constant pattern doesn't really apply to basketball. And then there's one more obvious thing, which we hadn't mentioned.
Is it just time? Or you have to stop playing?
Eventually there is a time limit. No, Brittany was ugly. Let me tell you. She did, I don't know what she did, but she was ugly, and we were just like, Brittany, we're taking your points away. Can we take Brittany's points away?
Heck no.
No. She either gets the points for the hit or she doesn't. Even if it was an ugly hit and she hit him in the foot and she told him she was sorry, like, she either gets her points or she doesn't. So we can't take points away. So all these little facts that we're writing about how there is a set number and we could easily count it, all this is why we know it's discrete. So tomorrow the thing's going to just have, the checkpoint's just going to have a couple of examples and you say, this is discrete and here's why. This is continuous and here's why. And then our last one is also pretty easy. It's high to a rocket after a launch. So we need to know why this is continuous.
Because
No
gravity.
No pattern is going to be the first one. So table 1, go ahead and get your point. Table 1. And then coming back to table 2, because of the gravity, just because the time is increasing doesn't mean the height is increasing. So time and height, I'm going to say they're independent. Because you would think like that the longer it had been, the higher the object was, but you know gravity means what goes up must come down. Okay, table 1 and then 4.
It goes, like, it increases, then it decreases.
It does increase and then decrease, which I kind of think I kind of got with time and height independent, but he's right. Okay, so if y'all think that's different than time and height independent, write it, and you both can have a point for it. I'm telling you, I'm free for points today. And then the last thing I would say that someone said last period, which is not on my key, so the fact that they had these own thoughts on their own is nice, and you probably would too, but I'm pushing you along. So, they said there is a measurable variable between each given point. Meaning, somewhere between 0 and 1, I was at 25, at 26, at 27 until I got all the way to 30. Somewhere between 1 and 2, I was at 34. There are a lot of wishy-washies in between with a continuous thing, whereas with a discrete, your ticket either costs $8.50 because you bought one, or it's $17 because you bought two. Like, it's a set thing of what you're going to pay. Okay, are there any questions about this? Again, we're going to have a checkpoint tomorrow. It's supposed to be an easy 30% grade for you. My God, let's pray it is. Instead of doing ACT prep, because I love you and you have been exceptionally good today, we're going to keep it real simple here at the end of class. Real simple. Will you go in the closet? There's a bucket that says scissors. You can go ahead and clean everything else up. If you would like to get him to cut your thing up. Okay, I'm going to take hers. She's getting scissors for me. So this is how you could lose a point today. This is really sad that you could lose a point by not doing this correctly, but it's possible. I need you to fold your paper hot dog style. Hot dog style. Yes, please. Once you folded your paper hot dog style, she is bringing you a pair of scissors. You need to cut along the slits, but you need to do so and not actually cut both halves of the hot dog style paper.
Wait, repeat that.
Let me actually show you. Look at mine. I have cut my slit and my other slit, and I'm going to keep cutting, but I'm not cutting through the whole paper. I need you to cut your paper like that. You're saying, Mr. Coleman, why would you take a point away for that? Because I promise you, here in this Greek, you got to learn how to be cute, and we cut stuff. You got to learn to be cute and cut stuff.
Yeah, I don't
Yeah, you took the street for a reason. You wanted to color and be cute and cut stuff. You knew you didn't, and that's why you're with me. You don't want to be cute and cut stuff? I like all that stuff, but I don't like color sometimes. Oh, you're going to love color.